Welcome to Spaceverse, your portal to cosmic adventures. Over the last several years, the James Webb Space Telescope JWST has produced unexpected findings that researchers have struggled to adequately explain. Starting with small red dot galaxies and progressing to early universe over massive galaxies, JWST has proven that spiral arm galaxies can exist earlier than thought, and it is continuing to test current theories of cosmic evolution. In a recent publication, Smethurst and colleagues from the Galaxy Zoo and related groups assert that they have discovered featureless, disc-shaped galaxies at an unprecedentedly early stage of the universe's development. This advancement revolves around Smethurst's research, which has been officially published and is now prepared for further examination. The definition and importance of featureless disks are the main topics of this discussion. It goes on to discuss how the Galaxy Zoo citizen science project was able to identify these galaxies in JWST data. Whether these galaxies are really featureless disks, or if their immense distance makes them appear that way, is another question that the approach considers. We conclude by discussing what these results mean for our future knowledge of galactic evolution in the cosmos. First, categorizing galaxy shapes is very beneficial from a scientific standpoint. It provides information regarding the events that a galaxy has experienced over its existence. This is similar to a fossil record. Has something happened to it, or is it now unstable, or has it combined with another galaxy and turned into a huge blob with a spherical shape? Scientists can now view farther away galaxies as they were when the cosmos was younger, like peering back in time, because light travels at a constant speed and takes time to reach Earth. This allows scientists to track the evolution of the universe's form across time by looking at how galaxy shapes change. When did the cosmos cool and calm down from its chaotic early years? This is a major topic that scientists are attempting to answer. The emergence of large, well-organized galaxies in the form of thin disks began at what date? The JWST has recently stoked researchers' excitement for the possibility of discovering barred spiral galaxies and other galaxies with large spiral features at previously unseen distances and epochs. These disk galaxies, these extremely tranquil and peaceful galaxies, began to emerge at that time well before any of the large-scale cosmological models had anticipated their emergence. However, there are studies that argue this is just because there aren't enough virtual particles per galaxy in universe-scale simulations to faithfully reproduce the physical processes that cause the shape of galaxies to change. It was discovered that the sole known simulation capable of producing disk galaxies during the early universe era actually produced featureless disk galaxies. So galaxies devoid of structure, extremely flat and thin, and constantly spinning. There isn't a central bulge, clusters, bar structure, or spiral arms. Nothing, just stars scattered over its flat disk. In most cases, a large spheroidal galaxy is the result of a merger between two galaxies and is characterized by a uniform distribution of stars. Then the object's motion is entirely at random. Like beehives in utter disorder, the stars are still in orbit around the center, but this time there is no discernible pattern. However, in the local cosmos, scientists have discovered disk galaxies with a uniform dispersion of stars and a good pattern of rotation. In order for that to have occurred, those galaxies would have had to have lived in total solitude, unaffected by anything. A spiral, bar, or even one of those central bulges would result from any instability circulating through the galaxy if this were not the case. Is it possible that these featureless disk galaxies, which are observed in the local cosmos, were also existent in the early, faraway cosmos? Can we trace all of the spiral galaxies we see today back to them? On the other hand, could they be the grand finale of an alternate galactic history? At what point in cosmic history do these featureless disk galaxies first become visible? For those who are curious, this researcher does not focus on disk galaxies but rather the formation and evolution of supermassive black holes. Indeed, the researcher focuses on studying isolated disk galaxies, which have never merged, to determine the specifics of supermassive black hole growth. Thus, knowing the origins of disk galaxies is crucial to comprehending the growth of black holes and maybe even their origins. The catch is that featureless disks get harder to see at larger distances without distinguishing features like spirals or bars, so it's not easy to answer that issue. Now we can turn our attention to how the Galaxy Zoo Citizen Science Project actually discovered these featureless disks in JWST data. The data utilized were images obtained from the Cosmic Evolution Early Release Science Survey (SEERS), a JWST survey of a tiny sky region designed to locate the maximum number of distant galaxies. A total of 7,679 distinct galaxies were spotted in the first round of data. And surely someone has to label the galaxies if they turn out to be of a specific sort given all that data. Indeed, the researcher might have taken the time to examine each of the 7,679 photos separately and identified the featureless disks. If the researcher had set aside, say, a week to devote themselves fully to the task, they would have finished them in due time. The thing is, we all make mistakes as individuals. Therefore, it is always preferable to have numerous individuals examine each image to obtain statistical agreement when analyzing data like this. More eyes on the content equals better results. Scientific groups frequently employ visual classifications performed by trained professionals. This is manageable for a sample size of about 7,000, but in most cases, it's just a small number of people. As data volumes increase, that approach will not work. There is more to come after the SEERS release. When future surveys expanded to hundreds of thousands, billions of galaxies, or even tens of thousands, what will happen? A combination of citizen science initiatives and machine learning algorithms, sometimes known as AI, has thankfully resolved this issue. After nearly 15 years, the Galaxy Zoo project is still going strong. The goal is to have 40 people classify each image of a galaxy that is posted for public use. To teach an AI algorithm how to perform the task, these categories are utilized. In spite of AI's tremendous progress, the sector still needs human intervention. It can't learn from little quantities of unlabeled input and produce accurate results. It was recently accomplished by this researcher and the Galaxy Zoo team using photos from the Daisy and Euclid large-scale surveys, which were previously announced on the researcher's channel. We need public support to keep doing this kind of research. At all times, the Galaxy Zoo website has pictures that are prepared for categorization. Each categorization, then, adds up to actual science, like the researcher's latest publication, so it's a good use of spare time. Here, the group managed Galaxy Zoo with data collected by JWST. As a consequence of 6,957 volunteers viewing SEERS photos on the Galaxy Zoo site between June and November 2023, a total of 311,000 classifications were made. Almost every one of the 7,679 galaxies had at least one classifier, and that number was 6,945 in all. Everyone who used Galaxy Zoo at that time, even if it was just to make a classification, has the researchers and the team's eternal gratitude for enabling this scientific breakthrough. Each galaxy gets a percent that shows how many individuals categorized it in a given way when all of the classifications are combined into a huge data table. For instance, in response to the initial question, 80% of respondents indicated that a galaxy had features, whereas only 20% indicated that it was smooth. In spite of the fact that does it have features or a disk, is the first question asked in each Galaxy Zoo version. Past versions have demonstrated that features are more influential in determining whether or not a galaxy seems to be flat disk. To be honest, not even specialists can tell them apart just by looking. While smooth, spheroidal, or elliptical galaxies tend to fade out from the center, disk galaxies typically have a clearly defined edge. Because of this, the vast majority of Galaxy Zoo volunteers will incorrectly label a featureless disk as a smooth galaxy, leading to the confusion of the featureless disks under consideration here with spheroid galaxies, which are inherently distinct from featureless disks due to their formation in the aftermath of galaxy collisions. So how does one go about separating the featureless CDs from the rest? Two paths can be taken. One is to visually inspect all of the galaxies once the list is reduced to those that were deemed smooth, or at least by the majority. The problem is that it won't work as the amount of data becomes more abundant. Another alternative is to use each galaxy's image to fit a model of the light's behavior. Is it flat, like a disk, or does it gently fade into nothingness, like a spheroid? Fitting a Circic index is what this is all about. The researchers enjoyed themselves in this investigation because they found out that those two things had already been done by another group of experts. All 7,679 galaxies had been visually categorized, and the following questions had been answered. Are these objects spheroids or disks? The researchers had also fitted models to the photos to determine if the galaxy appeared as a disk or a spheroid based on the light's behavior. This was a 23rd century article by Ferreira and co-workers. The researchers could use the volunteers' and experts' classifications to create a scatterplot showing which group was more likely to have identified a galaxy as a disk or a highlighted object in the galaxy zoo. There is a galaxy for every black on the graph. Although it is not featured, the top left corner is where the action is, and experts have classified it as a disk. Under the area's purview are 839 galaxies. From closest to farthest, 15 such instances were highlighted, arranged in ascending order from top to bottom. I had to verify first if they were, in fact, disks. Would a disk galaxy's light behavior be characterized by rapid decay? By comparing the distribution of the Circic index, which shows the rate of fall-off for both featureless and normally featured disks, a small value suggests a quick disk and a big number implies a sluggish spheroid, we find that the two types of disks are quite comparable. So it was likely that they were disks, according to the researchers. Locating the farthest of these seemingly featureless disks required a redshift factor of 7.35. A higher redshift indicates that the expansion of the cosmos has stretched the light to a greater extent. It is feasible to ascertain the distance of the galaxy at the time of light emission and the age of the universe at the time of observation by calculating the stretch, which in turn allows one to ascertain the time the light has spent traveling through the expanding universe. This galaxy appears as it did when the universe was just 700 million years old due to the light's long journey of somewhat more than 13 billion years, as measured by a redshift value of 7.35. After only 700 million years in existence, the universe has settled into a peaceful disk galaxy. Despite JWST's superior intelligence, field of view, and sensitivity, it can identify many more featured objects at extreme distances than the smaller Hubble Space Telescope. For example, the Space Telescope does have some limits. The resolution constraints of telescopes cause objects to appear smaller and fuzzy when one looks through them at higher distances. Now we need to know if these disks actually lack features, or if their seeming lack of features is just a result of their great distance from us. At that stage of the investigation, the first red flag was the increasing number of these seemingly featureless galaxies in the smaller and fainter population. It is possible to conduct some rough calculations here. What if, for example, JWST finds a population of nearby featureless disk galaxies of different sizes? What if, to make them look smaller, we artificially redshift them to make them appear farther away? Would JWST still pick them up? Based on the findings, it ought to be able to. The detection limit was indicated by the dashed line, and the gray area was the expected distribution of this galaxy population when artificially redshifted across the graph. Size alone doesn't explain why distant galaxies appear fainter or why early galaxies were smaller and dimmer. Full simulations are needed to model these complex effects. A 2024 study by Langang et al. Showed that bar features in galaxies drop from 100% nearby to 55% at redshift 3 about 11.5 billion light-years away, suggesting many early disk galaxies that look featureless may still have hidden structures. Still, about a third remain truly featureless, raising questions about galaxy evolution and the role of dark matter. Undisturbed galaxies stay disk-shaped, unless disrupted by mergers or internal instabilities. Some researchers suggest that in dark matter-dominated galaxies, visible features like bars may never form, as supported by studies from Fujian and Bland-Hawthorne. Normal matter predominates over dark matter in the Milky Way, according to observations. This is especially true in the region surrounding the Sun. The fact that normal matter has predominated in disks for the last 11 billion years is likewise well known. But how about in the interim? Further, in the case of a sample of disks devoid of features, what would happen? Future research could go in that direction, looking at the possibility that galaxies start out as featureless disks and only start to form structures like spirals, bars, bulges, and clumps when the ratio of normal to dark matter over a certain threshold. Furthermore, this finding has laid the gauntlet down for scientists working on models of the early cosmos and galaxy formation. To comprehend the existence of a featureless disk galaxy after just 700 million years in the universe, they need to determine what is currently absent from these simulations that hinders the formation of disk galaxies at such an early stage. If you enjoyed this journey into the early cosmos, don't forget to like, subscribe, and hit that notification bell so you never miss a launch into the latest space discoveries.